Hi, I'm Justine Kochi. I'm a senior software engineer for Microsoft. I work in the commercial software engineering group, which means I spend all day working with customers and helping them be more effective on Azure. Recently, I've been working a lot with Cosmos DB, so today we're going to go over some partitioning tips to help you increase performance and save money, two things that we absolutely love. Okay, so why does partitioning matter? As you know, Cosmos DB is a distributed database, and that means that your data is actually distributed across multiple physical machines. For the purposes of this presentation, we're going to refer to these machines as a physical partition. Now, you have all these different machines. How does Cosmos DB decide where to put your data? Which machine does your data go on? This is the crux of partitioning. So let's imagine we have an application for an IoT scenario. We have thousands of devices and they're all writing data to Cosmos DB. We have our container, which is partitioned by device ID. And so this is great. We have all of our devices sending data at a roughly even throughput. So we have this similar amount of data for all of our devices. They get mapped to one of these 5 physical partitions, and life looks good. Our data is distributed relatively evenly across all of these machines. Now, let's have another scenario. We have the same IoT application. It still has thousands of devices that are writing data to our container, but this time it's partitioned on day of week. So you can see we have 2 partitions which are almost full. They have a lot of data, whereas we have other partitions which are almost empty. We don't have our data distributed very well because, say, this particular application is in an area that's highly trafficked on weekends. So say Saturday and Sunday have far more data than the rest of the week. Additionally, you notice we only have 5 values, or we only have 7 days of the week, and there's 5 physical partitions. So we know that our mapping isn't going to be even. We're going to have some partitions that have far more data than others. So why does this matter? We know how our data is distributed across machines based on our partition key, but it also determines how your requests are distributed. So let's imagine we have a query, select star from C, where c.deviceid equals 123. So in our container, which is partitioned by device ID, we know exactly which physical partition to look at to get our data back. So we can do what's called a scoped query, or if we had the document ID as well, and we're making this request through the SDK, we could have a point read. Both of these scenarios are ideal. You know exactly where to go and look for your data. This is going to be the lowest cost and the highest performance way to access your data. But it's not always possible. Let's say we have our container partitioned on day of week. So we still have these 5 partitions. This time when we're asking for all documents where device ID equals 123, well, we have 123 in all of our partitions. So we need to check every single one to return data. Even though we are actually getting data from every partition, we still want to avoid this if possible. This is what's called a cross-partition query. And it could be possible that all of the data that we need is only coming back from a subset of partitions. We still need to check all of them because we're not sure where this data lives. It could be on any of them. So is that all you need to worry about, is making sure that you avoid cross-partition queries and your requests are good? Not quite. There might be other dimensions to think about. So let's think about how our requests are distributed in this scenario. It's very similar. We're still searching by device ID, but now we're also searching by day of week. So let's say we want to search for any given device ID, but we want to see the day of week is today. Maybe we're doing some analysis and we want to see is traffic picking up on Mondays. So in this case, every single one of these individual queries is still scoped, and they are spread evenly across all of our partitions. We're querying for a wide range of device IDs. It's likely that our request will be distributed. This is what we want. But back over to our day of week scenario. Now we have select star from C, where device ID is something and day of week is today. This query is also scoped, so it's not cross-partition. We know exactly where to look because we know what the day of week is. But in this case, we're always querying for the same value. So that one partition is going to be hit really hard, while the other partitions are just sitting there idle. They have excess capacity that's not being used. So how does this actually affect your workload? one of the other important things that partitioning determines is how your RUs are distributed. So let's say you have 25,000 RUs provisioned for this container. How are they actually divided across all of your partitions? It takes an even split. So in this case, we have 5 physical partitions, so they each get 5,000 RUs. With our container partitioned by device ID, our data is spread really evenly, our requests are spread evenly, so this 5,000 RUs is likely going to work for us. We're likely going to utilize all 25,000 RUs and get the most bang for our buck. But if we think back to the day of week container, we have really uneven partitions. Some of them are really full and are experiencing high request volume, where others are sitting idle. So even though we provision 25,000 RUs, we actually can only use that 5,000, right? All of our queries are hitting that one partition, whereas the rest of the partitions are idle. So now that we've taken a look at why partitioning matters, let's dive into what makes any given property a good partition key choice. Some of these points we've already covered. So first, you want a roughly similar amount of data for each of its values. Think back to device ID, where the frequency of writes is very even across all device IDs. They all have a similar amount of data, versus something like day of week, where weekends are heavier than others. And this really ties into the second point, which is you want a total high number of unique values. This is also known as a high cardinality. You want more unique values so that the likelihood that they're spread evenly across all of your partitions is higher. So think back to day of week, right? There's only 7 potential values, and they have vastly different amounts of data for each one. And when they're actually spread into our physical partitions, it creates a really uneven distribution. Next, you want to make sure that no individual value has more than 20 gigabytes of data. This is because that's the maximum amount for any logical partition key. So think Sunday, you can't have more than 20 gigabytes of data for Sunday. Now, if you do happen to have a key that's a really good choice besides this fact, there are ways to get around this with things like a synthetic key, which we will talk about a little bit later. Next, you want to pick a property that's present in all document types in the container. So say we have 2 different types of devices. We have maybe a motion sensor and a temperature sensor, and we're writing both types of documents into the same container. We want to make sure that the property that we pick is actually present in both document types. And lastly, you want to make sure that your value doesn't change. You really want to have a partition key that can spread your data evenly and isn't going to be constantly changing throughout any individual document. Okay, so this is all well and good, but let's take a look into a couple more specific requirements based on workload type. So first, if you have a read-heavy workload, it's very important that the property that you pick exists in most, if not all, of your queries. So think back to that device ID. We're querying constantly on device ID. We want to get either device IDs for today or device IDs in general. So this is a really good choice. Next, you want to make sure that you're distributing all of your concurrent queries across a wide range of values. Again, device ID did this really well, whereas day of week, we're constantly querying for day of week equals today. So all of our concurrent queries are hitting the same partition. Sure, tomorrow we'll query a new value, but then tomorrow, all of the queries again are against one partition. So this is something that we really want to avoid. In a write-heavy workload, it's a very similar concept, but it's kind of the opposite, right? So we want to make sure that we distribute concurrent writes across a wide range of values. Day of week is another good example for this. So if you're writing based on day of week, all of your writes for any given day will go to the same partition. This is going to create what's called the hot partition, and you're not going to be able to effectively use all of those RUs that you've actually provisioned for your workload. Okay, so I just threw a lot of data at you. Let's go through a real world scenario. So this is from a real customer that I've worked with in the past, and they had a product catalog. They have 2 different queries for this product catalog. The first is find products by store and by product ID. So this is looking up an individual item, say you want to get an inventory count or something like that. The second query is find products by store and by department. So say you're doing mass inventory for a whole department and you want to make sure that everything is in the right spot on shelves, say. So we look at this, we see these two queries. It's going to be a read-heavy scenario. It's product catalog. We don't get new products that often. So we're thinking, I see store in both of these queries. Maybe store is a good choice. But we need to dive a little bit deeper into the scenario before we can actually make our decision. So now what if I told you there's 500,000 product IDs? So there's 500,000 total products we could have in any given store, and we have 500 stores. So assuming that all of our documents are about 1 kilobyte, the maximum we could have is 250 gigabytes total. But now what if I told you some of these stores are really big, so they have all 500,000 products, but some of our stores are actually really small and they only carry a subset. And so we would have that uneven distribution of data. Additionally, if we look at 500 stores against 250 gigabytes, it's actually not that many unique values compared to the total possible unique values in our collection. We want to make sure that we have a lot of buckets so that all of these values can be mapped to evenly to all of our partitions. So now what if I told you the last piece of information, which is that the first query is run 1,000 times a second. Say across all of our stores, we have about 2 employees looking at products at any given time. So peak load is about 1,000. And finding products by store and department is run much less frequently, only about 50 times a second at peak load. So we're looking at store and we think, this doesn't distribute our data very well. So what can we do? You can actually create a synthetic key, and this will create more total unique values. This is done by combining 2 properties together that will better distribute your data and your requests, and thus will split your usage of RUs across more partitions. So you're going to get that better spread. You can actually use all of the RUs that you provisioned. So what does this look like? For this scenario, say we actually combine 2 properties, store and product ID, and we create a new property that we partition on. So this is great. For our particular collection, this actually creates a unique value. So this is unique per document. So what we can do is we can actually feed that value into the ID. So now we're making that the document ID. We partition on document ID, and this is ideal for our collection. It's a one-to-one mapping, one value per one document per value. We get the most even spread we could possibly have. It serves the bulk of our queries, and life is good. But we do still have some cross-partition queries. So let's take a look at another real-world example of a CRM system. So this is a customer management system. And in this scenario, we have 3 queries that are all run equally. We have find a user by their user ID, find a user by their phone number, or find a user by their email. And all of these queries are run at 200 times a second. So they're all equally important. We can't optimize for one over the other because we really need them all. So we're going to have some cross-partition queries if we pick any of these properties individually. So let's look at how much data is in each property. Maybe we can create a synthetic key and solve our problem again, right? Well, what if I told you we have 1 million user IDs, 1 million phone numbers, and 1 million emails? They're about 1 kilobyte documents, and we only have a gigabyte of data. It's not that much data. But if we try to combine any of these properties, it likely won't give us anything. We already have one unique value per document. Combining user ID, phone number, email is typically unique, so we wouldn't actually gain anything by creating a synthetic key in this scenario. So we're going to have a cross-partition query. And not only is it a small percentage of our workload, it's actually going to be about 2/3 of our queries will be cross-partition. So we really want to avoid that. Are there any strategies that we can take to mitigate this? And the answer is, of course, yes. So you can actually duplicate your data into a container with a different partition key that will serve each of your queries. And this is possible because storage is far cheaper than RUs in Cosmos DB. You're only being charged 25 cents a month per gigabyte of data. We only have 1 gigabyte of data. So if we can avoid those expensive cross-partition queries, we can actually greatly reduce the cost of our system by duplicating data. So let's explore what this actually looks like with our queries. We have our find user by user ID, find user by phone number, and find user by email. So all three of these queries are going to be served by three different containers. We have one partitioned by user ID, one partitioned by phone number, and the last one partitioned by email. So this works really well, right? There is one problem though. Now we have all of our data is in three different places, and we need to make sure that it stays up to date. We don't want any writes that happen to one container to not exist in the other containers. We want to maintain consistency across all of them. So there's a pattern using change feed that you can use to easily update all of these collections. You would have your writes going into one of the containers. In this case, let's pick user ID. And you can set up a change feed processor from the user ID collection to funnel those writes into phone number and also to funnel them into the email collections. So this does a really good job of keeping your consistency, your costs are still relatively low, and life looks good. But now, what if I told you something weird is happening and a bunch of customers are updating their data all of a sudden? So we have a lot of writes to this collection. And these writes are starting to get really expensive because every time we have an update, we actually have to replicate it 3 times. So is there something that we can do instead of duplicating that physical data 3 times? You can create a second container called a lookup container that has a mapping of the new key to the old key from the container with your actual data. This has a trade-off, so your performance and your cost goes down, but your complexity of the system goes up. But what does the system actually look like under this scenario? Let's optimize for just one of these queries for a minute, which is find user by email. So in this case, we only have 2 containers. Forget about the 3 containers from the last case. We have all of our data stored in one container partitioned by user ID. And we also create this second lookup container. So when we want to find user by email, let's say partition key equals whatever the email is, which is justine@email.com. And no, that's not my real email. Now, when we want to find user by email, we can do a request against our lookup container for this partition key, and we get data back. So the data that we get back is the actual partition key that we looked for, justine@email.com, and we also store that mapping for the old container, which is the user ID. Now that we have the user ID, we can do another scoped query to the container that contains our actual data, and we can get all of the user data back. So the complexity here is that every one query now becomes 2 separate requests to the database. We have to first request from our lookup container and then request from the actual container containing the data. But all writes only go into one place here. Of course, if a user wanted to change their email or change their phone number, we would have to go back and update our lookup collection, but those operations are far less common than changing, say, other information about the user. So in this way, we can kind of trade off this complexity to gain performance and cost. Both of these queries are now scoped, or could even be a point read if we include the document ID, and they're going to cost only 1 RU and have far lower latency. So we're able to reduce the latency of our overall system. Okay, so I hope that walkthrough of some of these real world scenarios and qualities to look through for in various partition keys was helpful. And I want to point you to a couple resources. The first, of course, is docs.microsoft.com. There's a lot of great information here about partitioning. I've linked to the partitioning overview, but there's tons of information here and further walkthroughs that you can do to help you map some of these guidelines to your own scenario. And I also wanted to highlight something called the Partition Key Advisor. So this is an upcoming tool that I've been working on with the Cosmos DB team for over a year now. And we're just about getting ready to release it via Cosmos DB notebooks. And what this tool does is it actually automates the selection of your partition key for you based on some detailed questions about your workload. And these questions mimic very closely all the qualities that we looked for in the beginning of this talk. And it has some logic in here to help you determine when is a synthetic a good choice, when do you want to duplicate your data or use a lookup container, some of these advanced strategies that we talked about. I've also included my real email address here. I would love to hear from you, especially if you're interested in using the Partition Key Advisor, being part of the initial user testing to kind of validate the engine. I would love to hear from you. Thank you so much, and I hope you enjoy the rest of Cosmos DB Conf.